Okay, so now I will be going over question 4. So the first important concept in this question is angular momentum. As I have explained before, there are two types of angular momentum. The first is when an object is just rotating around itself, and that an example for that is like the Earth rotates around its axis of rotation. And so that is the equation angular momentum equals moment of inertia times angular velocity. And the other type of angular momentum is when an object is rotating around something else. So an example of that is, say, the Earth rotating around the Sun. So that is angular momentum equals mv times r, mass times velocity times radius. In this question, we will be dealing with this type of angular momentum, which is just an object rotating around itself. The second important concept in this video is conservation of angular momentum. That's angular momentum. So the equation for this is that the initial moment of inertia times the initial angular velocity is equal to the final moment of inertia times the final angular velocity. And this equation is very important because it can help us solve lots of questions and is very important to the concept of angular momentum. Okay, so now I will read question 4. Suppose that a spherical star spinning at an initial angular velocity suddenly collapses to half its original radius without any loss of mass. Assume the star has uniform density before and after the collapse. What will the angular velocity of the star be after the collapse? Okay, so first what we are going to do, this will be conservation of angular momentum. But the first part I'm going to do is just calculate the initial angular momentum so we can plug it in. So the initial angular momentum is going to be moment of inertia times angular velocity. So for the moment of inertia, the equation is I equals mr squared, the mass, times the radius squared. In this problem, the mass is constant throughout, so we can cross it out just because it's constant. Okay, so the next part, so for the initial, we're just going to have r squared, because we have mass crossed out, times the angular velocity. So that's going to be for the initial. So we're going to plug it in over here for the complete conservation of angular momentum equation to solve the problem. So we're going to go r squared, that equals r squared times, and these are the, here, 1, 2, 2, forget that. So that is the basic equation we are going to be using. So in the problem, it says that suppose that a spherical star spinning at an angular velocity suddenly collapses to half of its original radius without any loss of mass. So this means that this stays the same, but the final radius is going to collapse in half. So like that, just radius is half what it was before. And okay, so we have that. The first thing that we are going to do is we're going to distribute the squared. So it's 4 times. Next, what we can do, this is also same radius, is that we can cross out the radiuses because they're the same. And then what we can do is we can multiply this both sides by 4. And that gives you the final angular velocity at the end. So in conclusion, the answer to this question is E. The final angular velocity is 4 times the initial angular velocity. And we were able to solve this by using the concept of conservation of angular momentum and angular momentum in general.